Hello, everybody. Welcome to part two of your midterm review for historical geology. We're going to be finishing up what we started last time, part one. Got all the way through igneous rocks, and we're moving on to sedimentary rocks. And we're about halfway, getting down here to, I think we have only 70 questions, so we're more than halfway done. So anyway, let's finish up what we started with sedimentary rocks. So you should know the different forms of sediment. What kind of things can constitute sediment? And let me clarify what I mean there. There are actually four categories of sedimentary rocks, and you might know that those four categories of sedimentary rocks correspond to four different types of sediment. Okay, so those four are actually listed for you down here. Clastic. There we go. Clastic, biochemical, chemical, and organic. So you want to know which each of those are made of. Okay, clastic is made up out of just weathered. Gosh, this is going so slowly. Hold on, let me try to close this and see if that helps. Weathered grains. Oops. I'm sorry. I'm trying to get this to work for me. Okay. Weathered, yeah, that's going faster now. Weathered grains. So these are made out of the clasts are just the stuff that gets weathered off of the bedrock, right? So it's the products of weathering. Maybe another thing you say, products of weathering. I'm just going to put WX for weathering. Biochemical, it's the remnants of marine life. So that comes from marine life, things like shells and tests. You might be like, what on earth is a test? A test is the little microscopic shell of plankton. You might remember this from the lecture. Plankton contributes a huge amount of sediment to the ocean floor. Okay, actually, believe it or not, when you go into the ocean, there are billions and trillions of little plankton swimming with you that have little tiny shells, and those plankton die, their shells sink to the bottom, creates marine sediment, which is biochemical sediment. Okay, so there's shells and tests of little microscopic organisms, or it could be large organisms too. Okay, you've probably seen coquina, which is made up of macroscopic shells of things like clams, oysters, etc. Okay, so that's a thing as well. Doesn't have to be microscopic. Chemical rocks are made out of chemical precipitates. Okay, precipitates. Precipitates are chemicals that are precipitated out of water. So think of water, it evaporates, and all of that material that is dissolved in the water precipitates out. Okay, so maybe you've done an experiment before where you took some tap water, you boiled it down, and there was some mineral content left over. Okay, that's the stuff that gets precipitated out, and we would call that stuff chemical sediment. All right, and eventually, over millions of years, that could build up. Think of almost like hard water buildup around your faucet or something like that. Okay, that creates sedimentary rocks, chemical sedimentary rocks. Last thing here is organic. So organic, you can actually, I know I only asked for, I didn't ask for 3. So organic is made up of organic matter. So even organic matter can eventually become sediment, make a sedimentary rock like coal. Okay, so that kind of, number 39 and number 40 are kind of similar, but it says you should know the difference between clastic, biochemical, chemical, organic, sedimentary rocks. Well, it depends what the sediment is made of, whether it's the weathered grains and products of weathering of broken rocks and pieces of minerals, that gives you the clastic rocks. Whether it's made of marine organisms, shells, and tests, that's a biochemical rock. Whether it's made of precipitated material that's come from maybe evaporating fluid, that would give you a chemical rock. Or if it's made of organic matter, that would give you an organic rock. Okay. Now, you should know the following sedimentary rocks, be able to say, just tell me a little bit about them, right? So you should be able to say whether they're clastic, biochemical, chemical. You should know their mineralogical makeup, okay? So some of these, not all of them, but some of these you should know the minerals that are involved, okay? I'll tell you what you need to know. So the clastic rocks are the following. I'm going to put a C for clastic here. Sandstone, shale, siltstone, breccia, conglomerate. Those are your clastic rocks. That means that they're made up of broken pieces of minerals and rocks, okay? They're mostly made of silicates. Gypsum, rock salt are the chemical rocks, okay? Those are made of, it's very easy, gypsum's made of gypsum, which is also a mineral. Rock salt is made out of halite, okay? So that's their chemical makeup. Chert and limestones are biochemical rocks. Chert is made out of SiO2 silica. Limestone is made out of CaCO3, calcite, and aragonite. It's made out of carbonate material. Okay. You should know also about diagenesis, cementation, and sedimentary rocks. So, sedimentary rocks undergo a process of diagenesis. Diagenesis is whatever process, whatever collection of processes that turns sediment into sedimentary rocks. Okay, they usually involve a few specific processes. Compaction, that's where you push out all the space. You take sediment, unconsolidated sediment, you compact it, you push out the air, you push out the pores, the pore spaces. Okay, you compact it together. Dehydration, that's where you push out. Now, not only are we pushing out the air, we're pushing out the water, baking out the water. Maybe these sediments are starting to get buried, the heat is building up. We dehydrate. Next is cementation. That's where we have some kind of fluid with a lot of dissolved mineral content move through the pore space of the sediment. It deposits all of that mineral content. It cements the rock together. Okay, so those are the three processes involved in diagenesis. That takes sediment, turns it into a sedimentary rock. Moving on to metamorphic rocks. What is a protolith and what is a metamorphic rock? So metamorphic rocks are rocks that have undergone solid state. A solid state is important. It means that it hasn't melted, the rock hasn't melted, but it's undergone solid state changes. It's altered, changed, metamorphosed under the solid state. So that means it didn't melt. Okay? If it melts, it becomes an igneous rock. What is a protolith? A protolith is the starting rock, the beginning rock. So it's what you start with. Okay, it's the rock you start with. So that could be a sedimentary rock or an igneous rock. Okay, some sed or igneous rock. And a shale, a siltstone, a basalt, whatever it is. It undergoes metamorphosis, and it becomes a metamorphic rock. Okay. Now, like I said, if a rock melts, it's no longer changes in the solid state. Even if it melts partially, it recrystallizes. It's going to be an igneous rock now, not a metamorphic rock. So if there's any melting, we call that igneous. Okay. What are some of the agents of metamorphism? Things that cause the metamorphism. It's pressure, temperature, and fluids. Okay. So hydrothermal fluids especially. Hydrothermal fluids are like hot water that's moving through the rocks, usually under the heating of maybe a magmatic body, an igneous body, some igneous activity that's nearby that can heat up the water very hot, cause metamorphism. Now, if you metamorphose a shale, what kind of metamorphic rock do you get with increasing metamorphic grade? So the metamorphic grade means more changes, stronger changes, so you increase metamorphic grade. Low metamorphic grade means that just slight changes have occurred. Okay, high metamorphic grade means a lot of significant changes have occurred. Now, if you start at a relatively low pressure and temperature, you're going to go from starting with a shale, you're going to go to a slate, then you're going to go to a phyllite, then schist, and finally a gneiss. Okay. How about if your protolith is a basalt? You get, again, a progression, but it's enough to just know maybe green schist. You start off with a green schist, and then you can go to an amphibolite. And even increasing, you can go to eclogite. And knowing any one of those is enough. So whatever is easiest for you to remember, green schist, amphibolite, eclogite, any of those, green's just is probably easiest. Any of those is sufficient to say. I just want you to know at least one example of a metamorphic rock in which the protolith is a basalt. What about limestone? That's marble. Okay, so marble is a metamorphic rock formed from a limestone. Sandstone is a quartzite. Okay. What are some changes that take place during metamorphism? You should be able to name at least 4. So there's recrystallization. What's recrystallization? That's where you go from small grains, they recrystallize, they get bigger, and you end up with larger grains like that. Okay? So that's recrystallization. You also have phase changes. You might remember we talked a little bit about polymorphs in this class. So polymorphs is a mineral that has the same mineral formula, but it has different atomic structure, different atomic packing. So often what happens is you go from atoms with, actually it might be useful to show you metamorphic rocks here. It's where you go from polymorphs. So I can show this slide even. Right? You go from graphite to a higher degree of pressure. It's going to cause a more efficient packing of the atoms. So you notice how diamond is more efficiently packed, like it takes up less space. So imagine you were packing a suitcase to go on a long trip. You had a lot of stuff to take. You can only take one suitcase. You're going to pack things in there really efficiently, right? So going from graphite goes under pressure, it becomes diamond. That's a polymorph. That's an example of phase changes. We call those phase changes. So the composition isn't changing. Graphite has a chemical formula of carbon, pure carbon. Diamond has a chemical formula of pure carbon. It's just plain carbon. But it undergoes really significant change. It's called a phase change. All right, so that's another example of a change that happens during metamorphism. What else can occur? We can also have what's called plastic deformation. That's when the rocks literally start to bend and fold and twist, kind of act almost like silly putty. They still stay in the solid state. It's not melting, but they'll start to develop folds. Maybe grains will become flattened. There's all sorts of changes that can happen like that. Let me show you an example here of this is a good example right here. You see how this rock has these layers, and the layers are getting all twisted and folded up, right? So that's plastic deformation. A final type of change that can occur is something called pressure solution. Pressure solution is when there's melting along grain boundaries, and you end up with flattened. Now this is different than plastic deformation, but you end up with flattened grains. And so you can see the example right here. You get these flattened. This is a conglomerate that has undergone metamorphosis and undergone pressure solution. And you can see how the grains now appear flattened. Okay, so pressure solution, plastic deformation, recrystallization, phase changes. There's even a fifth one that you could put down called neocrystallization. That's when new crystals form, new minerals form. Okay, all sorts of things that you could put down for there. Going on to plate tectonics, another important subject. For this midterm, I'm going to probably ask you'll notice there's quite a few questions from plate tectonics. Right, so you should know 4 lines of evidence that Alfred Wegener proposed for his explanation of continental drift, or his argument for continental drift. So there were 4 things, 4 arguments you should know. One was from fossils. That's simply that we find fossils of the same species on multiple continents that are widely separated now. Maybe they're separated by thousands of miles, and yet we find the same species. And sometimes we find the same species of a fern or a plant or a small marine animal, or not even a marine animal, a small terrestrial animal that couldn't have possibly have swam across like the Atlantic Ocean, for example. So that shows you, like, how did those fossils how did that species get so widely dispersed? And actually, it probably didn't have a very wide range. It probably just the fact that the continents have separated over time. Okay, so that was his argument from fossils. 2 is from matching coastlines. Alfred Wegener noticed, like a lot of people have noticed in history, that the shape of, for example, South America is almost exactly the same as the coast of Africa. So I mean, this would be the east coast of South America, fits perfectly like a jigsaw puzzle piece with the west coast of Africa. I don't think I need to explain that one. Usually people understand that pretty well. The third type of argument that came from Alfred Wegener for plate tectonics came from glaciation. So, Alfred Wegener was actually a polar climatologist. He knew a lot about glaciers and understood a lot about glacial movements. And he noticed that there's a lot of evidence for glaciers in places that are now equatorial. They're on the equator. And widespread glaciation. How did that occur in these places that are now, even during ice ages, they wouldn't have been covered with ice sheets and things like that. So it means that they must have been in areas that were colder, lower latitudes. That's what I mean. So the last one is matching mountain ranges and geologic units. So if you take a look, you can at a geologic map, you can find the same rock units, the exact same kinds of rocks on South America, on the east coast of South America, as you do on the west coast of Africa. Okay, so not only do they align and they fit together like a jigsaw puzzle, but you find the same fossils on either coast. You find the same kind of mountains on the same coast trending in the same way. You find the same rocks, exact same rock units on either side. It's a big indication that those two continents were at one time together. All right, so that's Alfred Wegener. So you should know that one, be able to answer, because that's a very common short answer question. It's on there. You might get it. It's kind of luck of the draw if you're going to get that question or not, but be prepared for it because it's on there. It's in the question bank. You should know the difference between the asthenosphere and the lithosphere. And I've asked this before already a little bit, but the asthenosphere is, if we draw a kind of cross-section of the Earth, we have the crust, and then we have the kind of top upper mantle, okay? And there's part of the mantle that is the lithosphere. And that lithosphere is hard and brittle and does not bend or fold or convect. Then there's the solid part of the mantle that is convecting, okay? It's able to bend, it's able to deform, it's able to move around. That is the asthenosphere, the no strength. Astheno literally means no strength, the no strength sphere, okay? So there's convection in the asthenosphere where the temperatures are hot enough, the pressures are high enough to let the rock, and it is solid rock, behave in a more fluid-like way over the course of millions of years. Okay, it doesn't behave in a fluid-like way over the course of a minute, but over the course of hundreds of millions of years, it does act very much like a fluid. You should know a little bit about the three different kinds of boundaries. So we have convergent, divergent, transform. Convergent boundaries are things like subduction zones. And when you have that, that's when you have a ocean coming into contact with a continent. When you have two continents coming together, you have continent. When you have those two things coming together, you get mountain building. So that's how you get these really high mountains like the Himalayas. It's from the subcontinent of India crashing into the continent of Eurasia, right? So that's how you get those very high mountains. You get very intense mountain building. That happens at a convergent continent-continent convergence zone. Divergent gives you things like mid-ocean ridges, MORs, okay? That's where the asthenosphere is welling up. It's causing a lot of volcanism, a lot of basaltic volcanism. You're getting spreading, you're getting extension. Those are the sorts of characteristics of divergent boundaries. Transform boundaries, on the other hand, you have earthquakes, you have faults, but besides that, that's where things are just moving side by side like that. But you really only have like faults and earthquakes. There's no mountain building. There's no volcanism. It's just maybe just faults and earthquakes. Okay, that's all you can really put for there. But that's not really too helpful because all of those boundaries have lots of earthquakes. Lots of earthquakes happen on every kind of plate tectonic boundary. All right, so for convergent boundaries, what's the difference between continent, and ocean continent? So ocean continent is a subduction zone. Continent, on the other hand, is something like when you have two continents crashing together, that's where you get mountain building, right? So we already kind of covered that in the previous question. You should be able to label a diagram of a subduction zone. So you should be able to, you're not going to be asked to draw this, but you could be given a diagram of a subduction zone and asked, what is, for example, you might have like, what's feature A? Okay, if I draw this, so this would be like the mantle asthenosphere. Okay, there's maybe the convection going on down here. Here's the mantle lithosphere. Here's the crust. This would be the ocean crust, the O crust. This would be the continental crust. Okay, right down here, this would be the trench. So you might have something that's labeled, and you have to say, it might be like, what is B? B is the ocean crust, for example. So that's kind of how that diagram would look. That's how that question would look on the test. All right, so you should be able to explain in a written response why we have volcanism at divergent plate boundaries, why we get volcanism at subduction zones. So this goes back to that question on igneous rocks of what causes melting in the mantle. Now, at divergent boundaries, right, here's your divergent mid-ocean ridge. Okay, so this is ocean crust. This is mantle lithosphere, and then here's mantle asthenosphere, and the mantle asthenosphere is welling up, okay, and it's causing the volcanism here, okay, so you have lots of volcanoes happening at this mid-ocean ridge. So why do we get volcanism there? It's because you'll notice right here that the crust is thinning and pulling apart. It's moving apart, it's diverging, and as it thins, it reduces the pressure. And remember, when you reduce the pressure, what happens? When you reduce the pressure on the mantle, it causes melting. That's called decompressional melting. If nothing else, if you just write for that question, decompressional melting at mid-ocean ridges, you're going to get a lot of credit for that, at least half. Okay? If nothing else, just remember the phrase, decompressional melting at mid-ocean ridges. What happens at subduction zones? If you go to a subduction zone, I'm going to use my drawing from up here, what you'll find is that the ocean crust that is subducting is releasing a lot of water into the mantle asthenosphere. Okay, well, what happens when you release water into the mantle asthenosphere? Do you remember when we talked about igneous rocks in the last video? I said that analogy. Whoops, this isn't a good pen. Let's use this. Salt is to ice as water is to the mantle. What does salt do to ice? Melts it, lowers the melting temperature. What does water do to the mantle? Melts it by lowering the melting temperature. The water gets in here, it acts as a flux. That means it lowers the melting temperature of the mantle, and that causes there to be melting. Okay, causes there to be melting, and you'll get volcanoes there. Okay, so if nothing else, if you can remember, just say flux melting at subduction zones. You get a lot of points. Okay, maybe not. You maybe won't get every point, but you'll get a lot of it. All right, you should know the various lines of evidence that support plate tectonic theory, and this is I'm talking specifically about the stuff that came after Alfred Wegener. Okay, we already talked about Alfred Wegener. We already talked about his 4 lines of evidence, but you might remember that we had things like magnetic anomalies. We had things so exploration of magnetic anomalies. We had echo sounding that mapped out the bathymetric depths, depth of seafloor. We also got radiometric dating, so we were able to date the age of the seafloor. Okay, all those things converged together to draw a very convincing picture of seafloor spreading. Okay, what did all those things prove? If you don't understand the details about it, it's okay, but at least you should understand that these all converge together to prove seafloor spreading. And seafloor spreading, if the seafloor is spreading and becoming larger and expanding, it can push the continents apart. And that provided the all-important mechanism that explained how continental drift could occur. Okay, for Earth's interior, you should know the four main shells of Earth, which are solid, which are liquid. Of course, the solid one, of course, that's the crust, the mantle, the outer core, the inner core. The outer core is the only one that's a liquid. Everything else is solid. Is there convection in the mantle? Yes. Is the mantle a solid? Yes. Solid state convection. Solid state convection happens in the mantle. You should have some idea about how convection in the mantle is related to plate tectonics. It causes plate tectonics, okay? The reason I talk about mantle convection so much is because mantle convection causes plate tectonics. We wouldn't have plate tectonics if it wasn't for mantle convection. Okay, so Earth history, this class would be very, very boring if there wasn't for mantle convection, because the Earth would just stay flat. It's the same, not changing. It'd just be the same. Okay, and we probably wouldn't even have continents. Continents, you need to have plate tectonics. All right, moving on to geologic time. So you should be familiar with the three types of unconformities, know how to recognize them in a geologic outcrop. So those three types of unconformities are the following. We have a disconformity. What's a disconformity? It's when you have layers of sedimentary rocks. Okay, so there's my beds of sedimentary rocks. All of a sudden, there's a break in the deposition, and then millions of years later, deposition begins again, and you get more layers put on top of the old layers, but there's actually a disconformity between those two right there. Okay, there's missing time. How do you recognize this? Well, it's pretty hard, and I wouldn't give you this one on the test, okay, because it's so hard to recognize. You would have to look closely and look for things like inclusions or erosive surfaces to actually prove this. So we can't, that's something pretty advanced. It's difficult. You should know it exists. You should know what it is. You should know what a disconformity is, but I won't ask you to recognize it in a picture. There's angular unconformity. So that's where you have the rocks kind of forming at one angle like that, or actually I should say that they didn't form that way because they're original horizontality, but you have rocks at one angle and then on top they're at a different angle. Okay, so that means that between the deposition of those two different series of rocks, there must have been a tilting event, and therefore there must have been an interruption to the depositional process, and that's what a unconformity is. It's an interruption. It's missing time in the geologic record. It is a break in the series of deposition. That's called an angular unconformity. The last one is a nonconformity. A nonconformity is when you have something like granite or a plutonic igneous rock or a metamorphic rock that is underlying sedimentary rocks, okay? And when you have sedimentary rocks in contact with the granite or this metamorphic rock, there must have been some kind of, like let's say this sedimentary rock unit is 100 million years old, and this is 90 million, this is 110 million years, and this is 120 million years, and this is 130 million years, 140 million years. You would not automatically assume the granite is 150 million years old, okay? Because who knows when that granite formed, right? It was obviously a stop or a break to the depositional process there, okay? So that's called a nonconformity. Now you will get, I shouldn't say you definitely will, because it all depends on luck of the draw and what you get from the question bank. But you could get a geologic cross-section like this one. All right. And you have to unfold and analyze it and kind of try to figure out what event came first, what event came last. This one is pretty close to what you might get on the test. Okay, it's not going to be super complicated, but you could have a series of events like this. How many events are there here? 6, 7? So this is what happened here. First thing I look for when I do one of these is I look for the thing that cuts the most. Thing that cuts the most layers. And that looks to me like fault J. So we know that if we go from youngest to oldest, fault J is the youngest because it cuts B, cuts O, cuts X, cuts D, cuts A, and it cuts M. Okay, cross-cutting relationships. The thing that cuts is younger than the thing that it cuts. So the stuff that was cut had to be there before it had to be there to get cut, right? So it's logical, right? Notice that M cuts a lot of stuff too. Cuts B, cuts O, cuts X, cuts D, it cuts A. So we know that M must have come before fault J. Next we have ADXOB, and they are in that order, okay? And you just go top to bottom, youngest to oldest. There's no tilting, there's no folding, there's nothing complicated going on here, so it would just be A, D, X, O, and B. And we know that from superposition. The thing that is on top is the youngest, the thing that's on the bottom is oldest. All right, radiometric dating. Please provide at least one isotope pair that's commonly used for radiometric dating. I am not going to ask you very specific questions about different isotopic pairs, okay? I'm not going to ask you, like, what kind of decay is rubidium-87, strontium-87, what kind of decay process happens in that isotopic pair. I'm not going to say that. But I could ask you like a short answer question just saying, please give me one example. It wouldn't even be a short answer. It'd be like fill in the blank, or like, I'd not fill in the blank, but just like open response thing. Just give me one example of an isotopic pair. And we talk about so many, right? We talk about rubidium-87, strontium-87. We talk about carbon-14. Well, carbon-14, nitrogen-14 are not used very commonly in geology, but I would accept it, I think. We talk about argon-40, potassium-40, argon-40. We talk about any of the uranium series, right? Uranium-238 to lead. Gosh, I can't even remember which one goes to. I think it's 211. Any of the uranium lead series. We talk about uranium-232 to thorium. There's so many different ones we talk about. So go back and just try to remember. If you could just remember one of them, you're going to be golden on that one. Now, what is an isotope? An isotope is an element that has a different mass number but the same atomic number. Okay, so that means it has a differing number of neutrons but the same number of protons. So, we gave a bunch of isotopic pairs up there. Ask about, but the important thing here is just that the mass number is different. Mass number is the number of neutrons plus protons. For atoms of the same element. Okay, and remember what defines if you're the same element. It's how many protons you have. Okay. Now, is radiocarbon dating useful, generally speaking, for dating rocks? No. The reason is that a lot of rocks don't have carbon. You can't do radiocarbon dating on something with no carbon. The other reason is that the half-life of carbon-14 is so short that it renders it kind of just useless. Because it only has a half-life of 5,700 years. How many half-lives go by in a million? There's 1,000 half-lives. So you split something 1,000 times, there's nothing left of it, or almost nothing left of it. All right, now what kind of rocks can be dated with radiometric techniques? You should know some of the nuances here. Generally speaking, igneous rocks. That's what it works on. Best volcanic, but plutonic is okay. Does it work on metamorphic rocks? Kinda. Metamorphic rocks, usually when you do radiometric dating on metamorphic rocks, you get the age of the last metamorphic event. So that could be useful. Sometimes we want to know when metamorphic events occurred, but a lot of times but it doesn't actually tell you when that rock officially formed, or originally formed, I'm sorry. Does it work for sedimentary rocks? Generally, no. There's one exception. Glauconite. Glauconitic sandstone. Sometimes you can get this sandstone called glauconitic sandstone. It has a lot of potassium in it. We can do potassium 40 dating, potassium argon 40 dating on it. And it can give us, because glauconite forms during diagenesis, it gives us a pretty good age of when that rock formed. Diagenesis occurred, created a sedimentary rock. All right, the atomic number of nitrogen is 7. How many neutrons does nitrogen-14 atom have? So the atomic number is 7. The mass number is 14. Because remember, whenever you say something like potassium 40, that 40 represents the mass number. That's the number of neutrons plus protons. So all you got to do is take 14 minus 7, which is the atomic number. That gives you the number of neutrons. Okay. So mass number minus atomic number equals neutron number. The half-life of uranium-235 is 0.7 Ga, gigaannum, billion years. If an igneous rock initially contains 100 atoms of uranium-235 and over 50% of these atoms decay, how old is the rock in billions of years? Well, what you have to realize here is that the half-life of uranium-235, 0.7 Ga. And if only 50% have decayed, what does that mean? It means that only one half-life has passed. And if only one half-life has passed, we know that 0.7 billion years have passed. Okay? That's all there is to it. So I don't know if that's a trick question, but you just have to reason through it. All right, final thing here, evolution and diversity of life. So a big part of what we study in this class is life history. And if you're going to understand life history, you have to understand diversity of life and the different phyla, different groups of animals, different kingdoms of life, etc., etc., etc. Okay. So I'd like you to know what are the major subphyla within the kingdom of plants. So the different phyla within plants. Okay, the big 4 major groups of plants. This is what I want you to know. So the 4 major group of plants. Plants is one of the 6 kingdoms. Okay, plants. We have, first of all, we have non-vasculars. These are things like mosses. After that, we have vascular spore-bearing. So these are plants that have vascular systems. That means they can transport nutrients and water throughout their tissues. However, they're not tissues, actually. I shouldn't call them tissues, but throughout the body. However, they do not reproduce with seeds. They reproduce with spores. These are things like ferns. So mosses, ferns. Next are gymnosperms. Sperm means seed. So gymnosperm means naked seed. It's a seed without a fruit. So these are the non-fruiting plants that have seeds. These are things like conifers, pine trees, basically. Angiosperms, the final group. Those are fruiting plants. Those are things like grasses, flowering trees, anything that makes a fruit like a vegetable, like a lot of the things we eat are angiosperms. Okay, so those are different. Anything with flowers and fruit, angiosperm. All right, now you should know those 6 kingdoms of life. Okay, those 6 kingdoms are archaea, and bacteria. Archaea and bacteria are both single-celled microbial life forms. You do not have to know the difference between them. I don't even know the difference between them. I know that there's a difference. I know there's an important difference. But to even understand that difference, you have to have a pretty serious background in microbiology. I do not have it. You do not need to know it to study historical geology. So we'll skip that. But there's archaea and there's bacteria. After that, we have protists. Protists are single-celled, but so archaea and bacteria are prokaryotes. Protists are eukaryotes. These are things like amoeba. There's some diseases that are protists, like things like, the name is escaping me right now. Malaria, and malaria is caused by, I can't even remember the name of it. I'm sorry. But things like rotifers. There are a lot of microorganisms that are eukaryotic, though. So they're very different than archaea and bacteria. Okay. Getting into single-celled things, plants, animals, fungus. The last of these to actually develop evolutionarily was fungus. Okay. More advanced than you thought. You might have thought, I know when I first started, I thought fungus would be like the lowest life form. It's not. It's most advanced, actually. So, not the most advanced, but it was the last to evolve. So, anyway, what is allopatric speciation? There's so many different speciation processes. I only ask you to know one in this class. Allopatric speciation is allo means different or other. Patric means like fatherland. Pater means father. So it's kind of a different fatherland. So what happens with allopatric speciation is that you have, let's say, a group of organisms, okay, and they're all living in this area, but then something happens, maybe there's a river forms, and it separates the two groups. And what happens is that conditions on one side of the river are sufficiently different than conditions on the other side, and you end up having divergent evolution. These two groups separate, they stop mating with each other, and they develop into different species. Once their sexual organs once they basically can no longer create reproduce. What happened to my? Oh wow, my looks like a word randomly crashed. I'm sorry. I'm gonna pause this so I can get my thing back. Okay, I'm back. Sorry, all my ink is gone now, or my drawings are gone because word crashed. So that's kind of interesting. But anyway, so that's allopatric speciation. Last two things here. You should know the difference between phyletic gradualism, punctuated equilibrium. Very simple. I know that these sound like very complicated terms. Phyletic gradualism and punctuated equilibrium are two different theories about how evolution has proceeded through life history. So phyletic gradualism just means that gradual changes have occurred little by little, and species have slowly changed over time. Versus punctuated equilibrium. Punctuated equilibrium means that species are actually the same for tens of millions of years, and then all of a sudden something changes. Maybe there's some big change to their environment brought on by plate tectonics or whatever, and there'll be a very sudden and fast change to a new species. So speciation happens very fast. So species are stable for a long time. Then there's punctuated by there's periods of equilibrium punctuated by these very fast speciation events. The reason that biologists like punctuated equilibrium better than phyletic gradualism is because it's very it's because the rock record and fossil record doesn't really give us a very good too many very good clear-cut examples of phyletic gradualism where we see very slow transitional changes and lots of transitional species between two end members. So usually that evidence is missing. Sometimes it's there, but often it's not. And so it seems like these speciation events actually must happen very fast because they don't appear in the rock record. So you should know the difference. Finally, final thing you should know is you should know the different phyla of the animal kingdom. Okay, and you should know kind of generally how to classify basic animals that you know and love. Okay, so there are a few important phyla you should know. First is Porifera. Those are the sponges, like the marine sponges, the animal. There are the Cnidaria, which are corals. Then, and also not only corals, but also stingrays. Stingrays, not stingrays. What am I thinking of? What are those? Jellyfish. Sorry, jellyfish. Yeah. It's late. I'm not thinking straight, am I? Also, sea anemones. Also, after Cnidaria, you should know there are some other things like Hemicordata. You don't have to worry too much about things. Roundworms, you like rotifers, and you don't have to worry about those too much. And the reason for that is that they don't appear very often in the rock record. So you could maybe include hemichordates. There's one important animal that belongs to that called the graptolite. And you're probably saying, what the heck is a graptolite? Never heard of graptolite. It's an extinct group of animals that is important in the Paleozoic, but we don't have them around anymore. Okay. Anyway, mollusca is very important, though. You should know mollusca. That's things like squid, octopus, a lot of things with shells like clams, oysters, snails. Okay, all those things are mollusca. Mollusks. Okay. Then we have arthropods. Arthropods are things like insects, crustaceans, crabs, shrimp, arachnids, spiders, scorpions, stuff like that. Things that have jointed, segmented limbs. We have the echinoderms. Echinoderms. These are things that have five-fold symmetry, like sea stars, sea cucumbers. There's these things called sea lilies that are very important in different parts of the Paleozoic. And then there's things like chordates, finally. Chordates is another important phylum of the animal kingdom. Those are things that have a neural cord. So you're a chordate. Dogs, cat, probably most of the animals you like are probably chordates. Okay, a lot of it's kind of funny because almost all the other stuff, maybe with the exception of with the exception of arthropods, are all things that live in the ocean. So anyway, those are the main groups though that you should know. I would concentrate on: Porifera, Cnidaria, mollusca, arthropods, echinoderms, and chordates. Okay, and just kind of know how to classify. You should have kind of some idea. You take an animal, know which of those groups to put it in. Okay. I forgot to mention one other kind of somewhat important group. It doesn't appear too much in the fossil record. Are annelids, and those are things like leeches and like earthworms. Segmented worms. They're basically segmented worms, which are different from roundworms like nematoda, which are round. They don't have segments. So anyway, that's all there is to it. Good luck studying for your test. Please contact me if you have any questions or concerns or whatever else. Anything you think I can help you with, please contact me. Talk to you next time. Good luck, and you have a good week.